Hello, in the exercise of Module 5, we will focus on the grid synchronization and specifically on the dynamic response of phase-lock loops or PLL. Here in the document, you can see some explanation about the model, which kind of model is provided. Then there are some explanation about the scopes. So let's first open the parameter file. You can always look into the parameter file. There are some parameters which are not used and can be removed. We can see that the parameters are available on the workspace. Then let's open the Simulink model. In the Simulink model, we can see a wind turbine is connected to a three-phase voltage source, which is modeled such that we have control on the amplitude, phase, frequency, and also the imbalances and harmonics. It's good to look into the model to know how the model is implemented. And by looking into the gain of the amplitude, we can understand the rated voltage is 33 kilovolts. So here in the model, the voltage with the desired amplitude is generated by this block. There are some switches that we can control the input to each parameter of this voltage source. So for example, for amplitude, we can have one per unit or we can define the other functions to have a variable amplitude. Similarly for frequency and also the phase, which is used here to model the phase jumps, and finally the imbalance and harmonics. By going into the wind turbine model, we can see that it consists of the filters and the converter is commented out. The measured voltage at the filter bus of wind turbine is input to this controller, but the controller is also commented out only in the ABC to DK transformation. PLL is the only one which is not commented out. So basically we can say that this is a block that is measuring voltage at the filter bus of wind turbine and is providing the measured frequency of and angle of this voltage using the PLL. We can do some formatting also on the PLL, so to make it opaque instead of transparent, so you see that now it's looks better, but it doesn't matter, it's just a format. And then we can look, as always, we can look into the mask and see how it is implemented. Frequency, for example, we can see the how it is measured, which components and filters are in front of the output frequency. And similarly for error, we can follow the signals. There are two outputs for frequency and same for error of the PLL. One is after being filtered and the other one is before. Also for automatic gain control, we can go inside this subsystem and see that actually this subsystem is providing inverse of the amplitude of the input voltage. And when we are multiplying it by the error of the PLL, it means that we are dividing the error by voltage amplitude, which is somehow normalizing error of the PLL respect to the amplitude of the input voltage in case the automatic gain control is activated. The variable frequency mean value, you can look into the parameters and see the description that it is averaging over a cycle of the signal based on the initial frequency. And also we can look into the subsystem to see how it is implemented. Then for the parameters of the PLL, we can see which parameters are used. As it is explained in the exercise document, derivative gain is set to 0, and you can look into the other parameter value. Also, the automatic gain control is enabled for the first part of the exercise. So as it is mentioned, this model is actually measuring the voltage at the filter bus of the wind turbine with this, but there is no converter here, so it is like an open circuit, and we are just observing the measured frequency and also the error signal of the PLL for different events. In the reference and measurement blocks, there are 4 scopes. One is VABC of the wind turbine. Other one is the frequency of the wind turbine, the raw frequency, which is not filtered signal. Then we have the frequency of the wind turbine measured by PLL but filtered. Then we have the frequency of the grid. For the amplitude, we have the measured amplitude of the voltage at wind turbine side and also grid side, and also the amplitude of the grid voltage. You can follow the signals to see where they are coming from and what is the difference between each signals by looking at to the corresponding go to and from blocks. So you can exactly understand which signal is plotted. And finally, for the phase, similar to the frequency, we have the unfiltered error signal, the filtered signal, and also the phase of the grid. Similar to other modules, we could put the parameter files to be run from the initial function. So we would not need to run it before running the simulation, and also preload function just to run the parameter files as soon as we open or load the model. You can look into the other callback functions here to know the usage, and probably in your future projects using these callbacks can save your time by making your model more automatic. So we looked into the model and discussed this part. Now, after opening and checking the models and parameters, we are asked to run the model with the given configuration and see the result. So let's set the required configuration. Amplitude needs to be set to amplitude sag. The frequency should be 1, and the phase jump, it's the multiple phase jump, and finally there is 0 imbalance on harmonic. Now we have the configuration. Let's run the model and see the result. We can see the measured voltage at the filter bus of the wind turbine, which is changing based on the voltage of the grid that is following a step change. Then we have frequency. In the frequency, we observe some transients, and the transient is same in all instances. The direction is different, but we can see that the amplitude of the transient is same. Here is the amplitude of the voltage measured by PLL and also of the grid. And finally, here we have the phase jumps. The transient that we were observing in the frequency was actually because of these phase jumps. Transients due to the phase jumps are similar. The direction is different depending if it is a step up or a step down. Also, there are 2 more transients which are because of the step in the voltage amplitude. So yes, the results are consistent. We saw that the error in the frequency and phase jumps were zero during a steady state after some transient. And the PLL response to the phase jump was not affected by the amplitude. We saw that in all instances, the transient response was same. In the next step, we are asked to run the simulation with similar configuration, but unchecking the automatic gain control of the PLL. So let's run the model with this setting. We don't expect to see a difference in the voltage, so it's almost same. But for the frequency, here we can observe that now the transient response of the frequency in different instances is different, which is dependent on the voltage amplitude. So it's kind of when the amplitude is high, we see a larger transient in the PLL response. And that is because we have removed the automatic gain control. Also, we can observe the amplitude of the voltage, which is following the amplitude of the grid. Finally, let's look at the phase. Here, the response of the wind turbine to phase jumps is different in different instances. For example, in the middle, where the voltage is the minimum, the response of the PLL has also the lowest transient. In the next step, we are asked to compare the PLL error signal for two simulations that we did, one with automatic gain control and one without automatic gain control, to have a better comparison between them. For this, we need to go to the data inspector. In the data inspector, the data that we are selecting are logged to the data inspector. For example, here we can see that the PLL error signal is chosen and is logged to the data inspector. So when going to the data inspector, we can see there are two runs, first run and second run. The second run is the newest, which we did by unchecking the automatic gain control, and run one is actually the first run that I did when the automatic gain control was enabled. Here you can compare and see the impact on the gain control. Also, we can look into the setting of the data inspector, especially the number of runs is important because it limits the usage of our storage for this data. Now here we easily can activate and deactivate each signal and see the comparison. Just as a hint, you can add other signals by selecting them and uh, choosing the log signals. Now let's enable again the automatic gain control for the rest of the exercise. In the next part, we are asked to investigate response of the PLL to frequency change. But if we go to the last part of this task, we can see that at the end, we need to compare the result of 4 simulations in the data inspectors. For example, let's run the model for multiple times. We already run it for 2 times, and now let's run it for 2 more times. Now we expect to see here 4 simulation at least, but it is limited to last 2 runs, and we have the current run plus 2 archived runs, which is 3 runs. That means that at least we need to make it 3 to make sure that we have the result from last 4 simulations in the data inspector. Now it looks everything is fine. We can also clear archive by removing the data. In this part of the exercise, the amplitude should be set to 1. The frequency should be multiple frequency change. There is no phase jump and also no harmonic or negative sequence. Now let's run the model and look into the result. We see that there is no step in the voltage. But for the frequency, we see the frequency of the grid is experiencing a step and a ramp, and we can see the transient response of PLL during these two situations. For the step response, we see the transient. For the step part of the for the step in frequency, we can see the transient response of PLL, and also for the ramp, we can observe the signals. There is a steady state error between the measured frequency by PLL and the frequency of the grid. And also for the voltage, there is a deviation here also, because the voltage is measured at the wind turbine filter bus, and there is a small voltage difference between between the voltage of the grid and the wind turbine filter bus. Finally, we can see the PLL error. For the step in frequency, the PLL error is removed after some transient, but when the frequency is changed as a ramp, we see that PLL is not able to remove the steady state error. PLL here is using a PI, and to be able to follow a ramp, we need a more complicated control design for PLL. In the next step, we need to design the PLL to realize different responses, which include natural frequency and also the damping ratio. In these cases, based on the explanation in lecture, we can obtain Kp and Ki of PLL. For a natural frequency of 10, the Ki is 100, and if we want to have a damping ratio of 0.4, the Kp needs to be 8. Now here we can see Kp and Ki are 8 and 100. Also, let's make the configuration as it is explained in the exercise, which is the amplitude of 1, frequency 1, and the single phase jump, and no harmonic distortion in these cases. So in this case, we can observe the response of PLL to phase jumps. Here, when observing these signals, one good point is to try to look into the signals. In this case, we design the PLL for a natural frequency of 10 radians per second. If we measure the frequency of oscillations here, we can see that it is matching with the natural frequency of 10. In the next part, we are asked to design the PLL for a natural frequency of 10 Hz again, but with a damping ratio of 1. The Ki will be the same, but Kp will become 20. Again, we can check it on the parameters of PLL. The values are detected, so we can run the model and observe the result. In this case, we see that the frequency is damped more, and there is not as much as oscillation as the previous case. In the next step, we are asked to design PLL for a natural frequency of 4 radians per second, which is less than 1 Hertz, and for a damping ratio of 1 again. For this case, Kp will be 8 and Ki will be natural frequency to the power of 2. We see the values are detected on the PLL block. After running, we can look into the signals and observe the result. Here we can see oscillations. If it was not damped, it has a lower frequency of oscillations, which makes sense because the design's natural frequency was 4 Hz. And finally, in the last part, we are asked to design the PLL gains such that it behaves as a first order filter. Again, based on the presented equations in the slides, we know that the bandwidth is defined by the Kp, and the Ki is half of the kp because alpha is equal to 0.5. After making sure that the values are detected on the PLL block and running the model, we can take a look into the result, especially the frequency and PLL error. There is no oscillations in this case, or it's very small because that was the aim here to act as a first order filter. Then in the last part, we need to compare the error of PLL for these last runs that we did. So we can rename the signals based on the runs that we did. Here in this exercise, we did the run and simulation for just a few of possible combination for the configuration that we have. You can always play with the model and play with the switches to the voltage source. That will help you to have a deeper understanding of PLL performance. Here we can see that we can see the response of PLL for different cases. In the first case, we see that the oscillations are observed. We can compare the oscillation frequencies and also the uh, damping or the overshoot undershoot of the signals, and see that the resultant response of the PLL is changed according to the design criteria that we were trying to obtain. So we can highlight the signals accordingly. You can compare the result here with the graphs provided in the lecture slides to make sure that the results are consistent with those graphs. And now we don't need to have those four signals, so we can reduce the number of archived signals and remove the additional signal. Last part of this exercise focus on the impact of harmonics and imbalances on the response of PLL. First, we are asked to observe frequency response versus the error signal of the PLL. Measured frequency by PLL is matching with the grid frequency without any steady state error, and the error inside the PLL is also zero after transient in this case. Now we are asked to introduce some imbalance and harmonics while keeping the voltage and frequency at nominal without any jump in phase. You can open the blocks to see how the imbalances and the harmonics are introduced, the timing, and so on. For the negative sequence, the order is 1, then the amplitude is 0.5 per unit without any phase shift, and the sequence is 2 because it's negative sequence. The timing also it's between 2 and 2.5. While for the harmonics, which is a 7th harmonics in this case, we have the order 7 and the sequence is 1, which because we are introducing a positive 7th harmonic, and the timing is between 4 and 4.5 seconds. Now let's run the model in this case. Here we can observe that there is no steady state error in the frequency, either the unfiltered frequency or the filtered frequency. Both of them are matching with the grid frequency, and the PLL error after filtering is also 0. But what about the PLL error without filtering? Here we can see that the PLL error without filtering is not 0. And if we zoom into these parts, we can see uh, there is some oscillations in the error of the PLL, and that is why that filtering of PLL is removing these uh, errors, because they are sinusoidal and averaging over the multiple period of these signals, because the window is set for a frequency of 50 Hertz and these oscillations are for higher frequencies. So the average value of these oscillations will be 0 and they will not be observed on the filtered error signal. We can also look into the frequency of these signals. The first part is due to the negative sequence that we introduced between 2 and 2.5 seconds. Here, if we measure the frequency, we can see that the time period of this signal is 10 milliseconds, which is equivalent to 100 Hertz. So now why it is 100 Hertz? The point is that in the PLL, there is that ABC to DQ transformation, and that ABC to DQ transformation has a shifting angle, which is the angle of the measured voltage. And the measured voltage, which is the grid voltage, has a frequency of 50 Hertz, which means it is shifting the ABC signals by 50 Hertz when going from the ABC to DQ domain. So that the grid signals which have a frequency of 50 Hertz will be observed at the DC values on the DQ domain. The negative sequence has already a frequency of minus 50 Hertz. If we shift it back by 50 Hertz, it will be 100 Hertz, because it's already is negative and we are making it more negative. So it will be 100 Hertz. Also for the seventh harmonic, which has a positive frequency of 7 multiplied by the nominal frequency, which is 50 Hertz, and is equal to 350 Hertz. We expect to observe a oscillation of 300 Hertz here, because the DQ signals in the PLL are shifted back by 50 Hertz, and the harmonic with a frequency of 350 Hertz will be observed as a frequency of 300. So if we measure the frequency of the oscillations in the error signal of the PLL using the cursor measurements in the MATLAB scopes, we can set the position of these cursors to cover one period of this signal. So almost it is one period now, and we can see that it is equivalent to a frequency of 300 Hertz, which means if there is no filtering inside the PLL, the error signal will not be 0. And we know the reason, because the PLL is shifting back all the signals by one fundamental frequency, so all the harmonics will be -1. So a negative sequence, which is -1, will be -2, and the seventh harmonics will have a frequency equal to 6 harmonics in the DQ domain of the PLL. We can also go inside the PLL to again see the signals. For example, the error signal of the PLL, specifically in this case, where it is measured. We compared the result in this simulation with the previous case, and also discussed about PLL error when there are imbalances and harmonics in the input signal. Finally, there are some homeworks that I recommend that you spend some time on them. The first homework is that in the result from section 3, you can measure the responses of the PLL, similar to what I explained, for example, about the natural frequency. You can measure the frequency of the PLL response. You can also see the overshoots and the damping, and they have a more detailed investigation on the result in these cases. In the second part of the exercise, you are asked to add a PLL to the reference frame model which was provided in the last module, because in that module we were giving omega t directly to the ABC to DQ transformation, but in reality this omega t need to be obtained somehow, and PLL is doing that and provides this omega t. So you can put a PLL and then give the different voltage signals as an input to the PLL and use the omega t, which is measured by PLL, as an input to the ABC to DQ transformations. So you can observe the impact of the input voltage to the PLL on the output of the ABC to DQ transformation, because the omega t is provided by PLL, so there is an impact, and we can here you will get a feeling that why it's important to choose the right signal for as an input to the PLL. So you make sure that your DQ signals are the signals that you want to have in your controller. In the third part of the homework, which is somehow a continuation of the part 2 of the homework, you are asked to look into the model from module 2 and draw the control diagram on a paper. That's always good to draw it on the paper and see which voltage is used for as an input to the PLL, and think about why the voltage at this point is chosen as an input to the PLL, and what is the impact on the controller of the PLL. For example, what would happen if we were giving the voltage of another point to the PLL. I think this is a very useful thing to do and think about, because it really gives you a good understanding of importance of PLL setting and the PLL design in the control of the converters. And this is the end of exercise for module 6.